This week, we interview Sharon Goldberg, an associate professor at BU, to discuss her paper on attacking the network time protocol and some of her other previous works on BGP and DNS. Security news this week covers drone registration, MongoDB password dumps, and much more. So stay tuned. Broadcasting live from G-Unit Studios in Rhode Island, it's the show where exploits run wild. Packets aren't the only things getting sniffed. Systems aren't the only things getting penetrated. Bits aren't the only things getting banged. And the cocktails flow steady. It's Paul's Security Weekly. Black Hills Information Security, the leaders in penetration testing and active defense. Email consulting@blackhillsinfosec.com to request a quote today. NetSparker, the developers of the only false positive free web application security scanners, enabling you to automatically identify vulnerabilities and security flaws in all of your websites, web applications, and web services. NetSparker scanners are available in 2 editions, NetSparker Desktop and NetSparker Cloud, the enterprise online scanning service. For more information, visit their website at netsparker.com/securityweekly. Looking for a career change? Tenable Network Security is hiring everything from programmers to researchers. Check out all of the available positions at securityweekly.com/Tenable jobs. Pony Express. Check out their line of penetration testing devices, including the Pwn Pad, the Pwn Phone, and the Pwn Pro. For enterprises, there's Pwn Pulse, providing continuous visibility into wired, Wi-Fi, and Bluetooth spectrums across all physical locations, including remote sites and branch offices. For all those hard-to-reach places, there's Pony Express. Visit them on the web at ponyexpress.com. Welcome, everyone, to Security Weekly. This is episode 445. I guess it's the Microsoft Networking Edition episode. I'm your host, Paul Sidorian. It's December 17th, 2015. This is our last show for this year. After this, we're taking a break, and there'll be lots of content that you can enjoy over the holiday break. For this show, as always, I'm very excited about our guest interview and all of our illustrious hosts that we have on the lines via Skype. In studio here, I am flying solo, although I am adorning my Pugtacular Christmas sweater. I guess it's an ugly Christmas sweater, but I don't know. Anyway. On the lines via Skype, we've got Mr. Carlos Perez from sunny Puerto Rico. Welcome, Carlos.
Hey, that's me. Hey, Paul.
How's it going?
Doing good. Doing good.
Mr. Joff Thayer is here on the lines from North Carolina. Where is it sunny in North Carolina currently?
It is not sunny in North Carolina. G'day, Paul. How are you? It's been raining all day here in North Carolina. So, is what it is. But it is warm. We're having a very warm winter in the east of the United States.
We are. It's wonderful. And also, broadcasting live from the Carolinas, Mr. Michael Santarcangelo's here with us. Welcome, Michael.
Home of the Panthers? Is that what happens here?
The Panthers, the Panthers are. We're having a good season the last I checked. So
yes, keep pounding Panthers.
You want me to send you some updates, Paul?
Well, no, I follow the Patriots, so
I know Tom Brady.
That's right.
Yeah, we can't help you.
I'm actually a Gronk fan. I think he's great. So.
Gronk is awesome. The Patriots. I've been a Patriots fan my whole life, dude.
And I still like you. That's
I got my Tom Brady Uggs on. I don't know. Can you see the Uggs? These are Tom Brady Uggs, dude. That's how much I love Tom Brady. Is I bought Uggs because he's a big Ugg fan too. He buys Uggs for all his fellow teammates. Which I
have a big problem with that because nobody in Australia knows who Tom Brady is, and Uggs are an Australian product. That's weird.
They are. C&M supporting your home country, Joff.
Yeah, well, there's some sheepskin producers that appreciate that.
I bet the sheep probably not so much.
Yeah.
Wow, how did we get there?
We started off strong tonight.
We did. A couple of quick announcements, which I don't have notes on. But B-Sides New York City is happening sometime in January 16th. So if you search for B-Sides New York City, it's happening soon. They've got a call for papers out there. And it's going to be right in New York City, which isn't too far from here. And Aaron, one of the guys that works for us, is very excited about B-Sides New York City, wants to make a trip. We'll see what happens. So hopefully we can be there and attend. It'll be a lot of fun. So B-Sides conferences are always fun, so make sure you check out B-Sides New York City. An update on the shop. If you're looking for Hack Naked gear, the shop has been shut down. There is no, if you go to shop.securityweekly.com, you will get a message that says you can try and email us and see what we have left in stock, but for the most part, we're sold out of most things, and we will return next year with a bigger, better shop with all kinds of fun stuff. But for now, we're taking a holiday break. We don't want to have to worry about processing orders. Hopefully you got all of your Hack Naked gear that you're giving to your family and friends for Christmas gifts ordered already, and let us know how that goes. If you gifted something with the Hack Naked logo on it to someone this year, we want to hear about it. Email psw@securityweekly.com. Sharon Goldberg joins us via Skype. Sharon, welcome to the show.
Hi.
Sharon, tell us a little bit about what you do and what your current role is.
So I'm a professor at BU, and I'm part of a group that does network security and crypto research. In particular, what me and my students are most interested in is kind of the plumbing of the internet. So BGP is the thing that I've been working on for the longest. We started looking at DNS a couple of years ago after the Kaminsky attack. I just love that attack. I just think it's so beautiful. And after learning about that, I started getting into DNS. We've done like one paper on that. And then this year, we were working on some attacks on BGP, and we were failing to do them. And then my student, Anshel, was kind of thinking, like, how can I do this attack? And she decided she would just change the clock and basically attack NTP, and she came and showed me this, and I was like, wow, that seems pretty useful. So we started learning about NTP, and so we've been working on that for about a year as well.
Nice. Now, how did you get interested in computer security?
I used to work in networking. I started probably 15 years ago working in networking, like back where they had FDDI and stuff like that. And then I worked for Bell Canada. I worked for the power company in Toronto. I was in the telecom group there. And then I went to grad school. I worked on optical communications, and somewhere through grad school, we were trying to use fiber optic communications to do encryption, and I realized I didn't know what encryption was. So I took a course on cryptography, and that was the end of optical communications for me. I had to start working on crypto. And then I realized.
And did you have a strong math background going into it? Were you always fascinated by math?
No, actually. So I'm an engineer. I'm not a mathematician at all. That's why actually I ended up in network security, because I realized all the cryptographers were smarter than me and better than me at math. So I started doing networking and crypto. And at the time, there weren't that many people in academia working on network security. So it was sort of weird to do both. And now there's a lot more. So yeah, but so I've been more, my background is more engineering and networking, but I do have this crypto background that I picked up 10 years ago as well.
So your paper on attacking the NTP protocol got some press. So give us kind of an introduction as to some of the highlights from your paper on NTP.
Okay, so I think what's interesting about this paper is like NTP is a protocol that nobody thinks about, but everybody uses. And, so even something like BGP or DNS, which we think of as really underlying everything on the internet and in the background, and we don't think about it. All these systems really rely on, encryption, SSL encryption, all of these systems really rely on time. In cryptography, the way we deal with stale keys or replay attacks is usually to do timestamps. And I've always kind of known that NTP wasn't secure, like it wasn't necessarily cryptographically authenticated or anything. It's usually sent without any crypto. Most commonly, I kind of knew that in the back of my mind, but I never really thought about it too much. And then after several years of working on different projects, in particular, we were looking at the certificate infrastructure that's being deployed now to secure routing, which is the Rpki. And that has this object that lives for about a day or 2 days. And sort of the security of the whole system really relies heavily on this object. So I'm sort of like, okay, every day or 2 days, so that seems like you need to have a good clock. And it just was kind of lurking in my mind for a long time. So when we started looking at NTP, we kind of thought that it would be very simple just to, if you were doing a man-in-the-middle attack, to change the time and just intercept the communications, change the time, because most of it's cryptographically unauthenticated. And it turns out it's actually a lot more complicated than that. NTP is very complex. It has a lot of different algorithms that are used to actually set the clock. So it's not the case that if you're using a full NTP that I send you one NTP message and I change your clock. That doesn't happen. So there was kind of a lot of work that we had to do before we were able to actually do any attacks that changed the time. It took us a long time to kind of understand how to do that.
Yeah, I was thinking it was as easy. Like when I was a systems administrator, I was actually doing a vulnerability scan of the network, and lo and behold, every NTP service on the network had crashed. And it was some weird vulnerability that like they thought they patched, but they didn't. But it turns out that like crashing NTP on all these systems was a huge deal, and it caused all kinds of problems. And I kind of took a lot of crap for it.
So the daemon just shut down completely.
Yeah, the daemon just core dumped and crashed. Yeah.
That can be bad. The cool thing though about the NTP daemon is if you try to mess with the clock a little bit and you're not smart enough about it, it'll just ignore you and just sit there, and it won't update the clock. Okay. So if you crash it, you can do things, but if you don't crash it, just kind of sits there. And that's why you sometimes see things like NTP servers that haven't been updated in 10 years. They're working fine, you know. They've got like, you know, they're taking time from, let's say, 5 or 10 sources. Like these are servers that I've seen. Let's say it's taking time from 8 sources, 4 of which have been offline for how many, like who knows how long, like years. And nobody noticed, you know, because there's 4 other servers, they're all fine. And, you know, NTP does a good job figuring out what to do in those situations. So that's a really interesting and kind of, it makes it more fun to try to study how you can attack the system.
Yeah, I mean, much like BGP, there's a lot of resilience. Whoa. There's a lot of resilience in NTP, similar to the way BGP and other in DNS work as well. There was an attack on the root servers on DNS, and for the large part, no one really noticed.
Right.
So Sharon, let me ask you. So my understanding of NTP is a little bit dated now, but it hasn't changed a lot to my knowledge in years. There's a stratum process where servers get to elevate from the default stratum 16 and then eventually settle into their synchronized state. In your research and your work with your group, was it that algorithmic process that you had to exploit to sort of become a valid peer before you could change the clock?
No. So we had 2 kinds of attacks. So one attack that we looked at was changing the clock. And the way we did changing the clock was with IPv4 fragmentation. So it was a really crazy attack. You're off path. It's a complete off path attack, so a remote attack. But what you need is for the server and the client to use certain IPv4 packet fragmentation policies, which we did actually measure for. We scanned for these on the IPv4 address space, and we did find several servers that we found like 20,000 servers that had this type of behavior. And then we could do an off-path time shifting attack. So that's how we exploited that. It wasn't really doing anything to the Stratum relationships. The Stratum relationships, basically, if you have an NTP client, let's say, and it's configured with several servers, whichever server it chooses to take time from, let's say that server is Stratum 3, then your client will become Stratum 4. And typically the Stratums are pretty stable, but I might be configured, let's say, with a couple of Stratum 2s and a couple of Stratum 3s, and I will choose between them, and then my Stratum might change dynamically. So that actually does happen. But we weren't really exploiting too much of that. So when we do our fragmentation attack, what our attacker will do is it will exploit the fragments to tell the client that it's a Stratum 1, because Stratum 1 is the top, the root of the hierarchy, and it's always better to be Stratum 1, so we can kind of encourage the algorithms to prefer our server over the others. So that's one thing that we can do. Our fragmentation attack basically takes the entire NTP packet and just overwrites all of it except for one part, which is basically a random number that the server needs to reflect back to the client. So it's a nonce. So we overwrite everything except for that one nonce. And then in that way, we can, from off-path, shift the time, change the timestamps and everything that we need to change.
Now, using overlapping fragments in order to do that?
Yes, we are. Yeah.
Okay.
So overlapping fragments are
so in environments that are dropping fragments at the perimeter, then your attack would be not effective, right?
Right. So it's interesting because So yeah, so you definitely want to drop overlapping fragments, and this attack will not go through. It's interesting because I don't know if you know about some of the earlier works on intrusion detection. Like 10 years ago, they were showing that you could circumvent intrusion detection systems by using
Yes.
IP fragment
Yes, I am
overlapping.
aware.
Yeah, very
Yeah.
familiar with that.
So
Actually,
super
10 years ago, I was
cool work.
researching that. Yeah.
Yeah, it's super cool, right? So I think some of the reaction to that work was that the firewalls should be reconstructing the packets and then scanning them after that. And so some devices, I believe, will actually reconstruct fragments and then scan them.
In pretty
Yeah,
low,
the
in pretty
virtual-
low bandwidth environments, that's feasible. When you talk about gigabit networks that we have today,
Yeah.
that starts to be really difficult.
Yeah, it's the IDS IPS world is virtual fragmentation reassembly and multiple threads to reassemble fragments and make sure they're fully inspected before you drop them back on the wire. And the idea there was the evasion was possible if the fragmentation reassembly policy differed between the IDS or IPS of choice and the endpoint itself. So that's where you got got your advantage. But plenty of environments that I've defended in the past, what we would do is just drop fragments entirely at the perimeter, not even accept them.
Doesn't that break stuff though?
It does break some stuff, but you'd be surprised. In a world of predominantly Ethernet today, it is not so much of an issue
because the frames are so big, right?
Yeah. In the world where we had a lot of mixed media back in the days of old, yeah, it would have been an issue, but it's not so much now.
But especially overlapping fragments. Like, you really shouldn't be seeing overlapping fragments in a normal situation. It's probably a sign that you're being attacked. So I very little reason to actually reassemble overlapping fragments. So that's for our off-path time shifting attack.
Okay.
We had a different attack as well, which was a denial of service attack. And this one was the CV that they fixed in the release of NTP that came out on the day of our paper coming out. And the reason that this attack, I think, was the most serious from the perspective of the NTP developers was that basically I could turn off NTP on your computer with one packet. So that's our kiss of death attack. And I didn't name it that, actually. So NTP has a packet of message format called kiss of death. And I didn't name that. It's in the RFC. You can check.
I didn't.
Yeah.
Oh, nice.
I need to go reread the RFC now.
Yeah, the RFC's fun. You should read it.
They're fun to read if you're looking to go to sleep, right?
No, I like reading RFCs.
I do too. Certain ones.
So if you look at this, the RFC, there is a packet called Kiss of Death. And we were like, what does this packet do? So what it does is if you're bothering a server too much, so in NTP, there's a client-server relationship, and the server has to maintain this long-standing relationship with the client. They're just constantly exchanging messages. It's a pretty low rate, like minutes or something like on the order of minutes usually. But you're just constantly engaging with this server. So these servers basically need a way to deal with too much traffic, and so they came up with this technique, which is the kiss of death, which I don't think I've seen in any other protocol. What they do is the server will send the client a packet that's called a kiss of death, and the packet has a pull interval. So pull interval is the time between how often you query the server. So what the RFC says is when the client gets a kiss of death packet, they should lower their rate and stop querying the server so often. And what the implementation does is it looks at the polling interval and it makes sure that the client doesn't query the server for at least the polling interval. It's actually more than that in some complicated formula, but bottom line is longer than the polling interval. Now, the cool thing about the polling interval is that it's an 8-bit field, and the poll is 2 to the value of the field. Okay, so if I put 25 in there, I get, I think, 1.5 years. If I put 17...
Kind of like TCP window scaling. Yeah.
Yeah, but it's like on the order of much longer than TCP windows. So, if you put like 6 in there, I don't remember how many minutes that is. Maybe 15 minutes. But if you put 17, it's 36 hours. If you put 25, you're getting up to years. And that field is actually 8 bits long. So when we did the study, we discovered that the maximum value for that field is 17, which is 36 hours. So that's already pretty good. I can send you a kiss of death packet and keep you quiet for 36 hours. So when we looked at the actual implementation, it turns out that it doesn't check that it's at least 17. So you can probably do more than that. Like you could put in 25, but we didn't test for 1.5 years because we didn't have 1.5 years. So I don't know if it actually works, but I don't see any reason why it won't work. We only tested for 50 hours. So basically, if you get a kiss of death packet, you'll be quiet for as long as the server tells you. Now, the thing is, it turns out that remember I was talking about my fragmentation attack, our fragmentation attack, and I mentioned that what we do is we overwrite all of the packet except for this nonce that the server reflects back to the client. So that's the case for all of NTP packets. Check for this nonce to make sure that they match, and it's basically 32 bits, so it's a little bit hard to spoof from off path. But it turns out that the kiss of death didn't check this nonce, so ignored the nonce. So that means I can basically, like, if I can do source IP spoofing, I can send you that packet, just like from any.
So you can spoof that from anywhere and basically tell any client to ignore NTP for theoretically 36 hours, but maybe implementation specific
not
longer.
I've tested 36. We've tested 36 hours.
Practically.
You can probably do longer. You can do longer.
No, is that implementation specific based on the developer's interpretation of the RFC, or for the most part? Like
now we need to talk about like how NTP software is.
Yeah, okay, I do. I want to talk about that.
Yeah, so there's the RFC. What the RFC says is you need to lower your rate. That's all it says. Now,
love RFCs and how non-specific they can be.
NTP RFC is really not very specific about a lot of things. You'll find if you read the RFCs, there's a lot of sort of like gray areas and you know, like one thing that drove us crazy. There's this thing called root delay or root dispersion. And it's this quantity that's used in all these algorithms for very important things. But the actual definition of this parameter changes from version to version of NTP, and it's different in the RFC. And we were like, what does this thing actually mean? But it's just different. So that's kind of how this ecosystem is. There's the RFC, and then there's the actual implementation. Now, when it comes to the implementation, there's NTPD, which is called the reference implementation. And that's what we tested.
Okay.
So, and there's various versions of the reference implementation. And through my sort of dealings with this is that it seems to me that there are a lot of, and I'm not the expert on this, but there seems to me that there's a lot of operating systems that kind of took NTPD and kind of forked it themselves and they're patching it themselves, you know.
Oh, that's absolutely the case.
And then there's the actual reference implementation. So you see things like NTPD 4.2.6, different versions on different OSs, and then the actual like official version is 4.2.8. So when you ask about like, was it implementation specific? It was in the reference implementation up until the very last release, which was NTPD 4.2.6 P4.
So unless someone fixed some of the issues that you pointed out, right, specifically.
Yeah. So unless so if you took the reference implementation, you didn't catch this, then it's in there. So if you hadn't forked and caught this specific issue. And the other cool thing about this attack is that you know, we can spoof the packet to make it look like it comes from your server, but then you should ask me like, but wait, how do you know what server the client is using, right? How do I know that? So the other cool thing is that NTP, the daemon by default, if you send it a time query, like if you say, hi, I'm a client, I would like the time, then it will tell you its time, and it'll also tell you what's called the reference ID, which is the server from which it got its time. Okay, so I can query you, and you'll basically tell me who you're getting time from. So now I know your server. I spoof a packet from your server, it's the kiss of death, and you stop querying that server, right? So now two things can happen. Either you just sit there and you don't take time anymore because that's your last server and you're done, or you have another server, in which case you'll synchronize to that server, and then I'll query you later. You'll tell me, oh, here's my other server, right? And then I'm kiss of death that one, and I just continue like this. So you can learn the servers, and you can basically turn them all off.
And also from a server, you can learn clients too, correct?
That's from the monlist command. So do you remember the NTP denial of service attacks from a couple years ago or a year ago? I guess 2014. So what was going on then? So NTP likes to expose a lot of information. Actually, there's So there's this query called monlist, and what monlist will do is it'll tell you all of anything that have queried you for any reason. So anyone who sent you a monlist request, anyone who sent you a time request, various different kinds of packets, and it'll just send you back a long list of who these queriers are. And so if the servers is returning responses to monlist, then you can learn the clients. The thing is that in light of all the DDoS attacks, most servers have been patched to not respond to this query.
I see. So several years ago, I exploited, my friend Bob exploited an attack because there was a particular brand of wireless router from Netgear that accidentally like fat-fingered or hard-coded an NTP server from a university inside of their wireless router firmware. I don't know if you read about this attack, Sharon. Yeah. So all of these routers start querying time from this university's NTP server. And
that's probably why they introduced the kiss of death.
Yeah, you're probably right.
Probably.
But this particular Netgear wireless firmware for this wireless router contained vulnerabilities, as do most firmwares for wireless routers. And a nice way to get a list of a bunch of vulnerable routers without scanning the internet was just to query that NTP server and spit back its list of clients. And you'd get a list of I got a list of 20,000 IP addresses that were all probably vulnerable Netgear wireless routers. That was a Metasploit module a few years ago. But what you're saying is in light of recent attacks, they've turned that functionality off.
They've turned that functionality off. I would say if you're running an NTP server, I would not allow any queries for anything remotely because you just don't want to expose yourself. There's other kinds of queries that you can still do on several servers. Like we did these scans for this query called RV. Mm-hmm. I think it's something like version. I don't know what it stands for, but it'll tell you the version of NTPD that the client is running. It'll also tell you the OS. So a lot of them will say this is NTPD 4.2.6p4 and the OS is Linux 3.1, so you'll just, whatever. So you'll learn a lot about the actual, the system that the server is running on, then you might be able to use that for other exploits. For us, it was kind of useful because we were trying to measure the NTP ecosystem. That was another part of our paper, just to see what versions were out there. Mm-hmm. I want to see, I think, what's interesting is the most popular version, I think, is almost 15 years old. I just want to confirm that.
Wow.
That sounds about right.
It probably hasn't been touched in that time.
Yeah, so 4.1.1, we found about 2 million servers.
And one of the surprising things is it's only one developer maintaining right now OpenNTP.
I was going to ask that. Who develops the base code for NDP?
It's the Network Time Foundation. So there's Harlan Sten, who's I don't know what his title is. I think it might be lead developer. But then there's several volunteers who do development on the team in there as well. There's there's also Crony, which is another implementation which we didn't test. But the lead developer there, Miroslav, he's awesome. I interacted with him quite a lot on some of the results in our paper.
Yeah, how was he to deal with when you came to him and said, well, we found these problems? Was he pretty open to your research?
Everyone was, thank you, please. Even, actually, we got to talk to David Mills, which was, he's the inventor of NTP, and that was really cool. We had a call with David Mills, and he said, this is great, we're glad you're looking at this. So they're very, very...
That's refreshing. Yeah, that's really awesome.
That's awesome.
Yeah, it's more IETF style, they're very receptive to seeing vulnerabilities. And this actually was, the reaction was we need to patch this. There was very little pushback.
There was no drama. That's great to hear. Yeah,
that's good to hear. Yeah.
So Sharon, if you can shift time on a system, what other attacks does that then lead to?
Right. So I think the most interesting one would be sort of changing certificates. After we wrote the paper, we discovered that there was Jose Salvi in Spain. He presented at Black Hat. He actually did implement some of these attacks on SSL certificates, so getting you to accept an old certificate because he changed your clock. He did that not on the full NTP, he did it on versions of NTP. So the other interesting thing about it is a lot of operating systems don't really run the full NTP, so all the wonderful things that NTP does to kind of make it really robust against attacks and all these problems, a lot of operating systems will actually, if you send a query and they get a response, they'll okay, that's the time, done. So he did attacks on those types of OSs, and he showed that he could do time shifting and actually get you to accept old certificates for Gmail. I think he showed that. So that's the sort of the one that you most think about because certs are really, really strongly relying on time. Anything kind of that uses crypto relies on time. So I'm interested in DNS. So there's DNSSEC. There you have signatures that expire in the order of months. So if you could shift time by months, you can affect things like that. We also there was work published on Bitcoin. So Bitcoin has timestamps as well, and those are on the order of hours. So if you mess around with the timestamps, you can kind of shift the blockchain backwards and get a miner to start mining an old version of the blockchain. And that's called time jacking. So there was a developer who, actually I don't even know because he didn't put his real name, or she didn't put her real name. So it's someone with a handle that published this. And then also, if you think about Kerberos,
very time sensitive.
Tickets, it's ridiculously time sensitive, right? So it's replay attacks. They just basically don't have any replay protection except that they have this short window that you're not supposed to be able to do replay in, and there's a little timestamp there. So, for example, you can't use your ticket for more than 2 minutes. Let's say there's a timestamp. So, and there's nothing other than that to protect you against replay. So if you shift the time, you can start to replay old tickets. So there's all different kind of orders of the attacks. Like for certs, it's orders of years. For DNSSEC months, Bitcoin is hours, and like Kerberos, things like that. Minutes.
How easy is it? Go ahead, Carl.
Okay, another one would be in TLS. I've seen certain appliances that if they're not able to validate TLS, they'll default to clear text. So one of the things you would do is you modify the time. The connection in TLS will fail, and it will then default to clear text. And now you've found a good way to downgrade that client.
Right, and similarly, what Jose Salvi was talking about in one of his even earlier papers, I think at Black Hat, which is like we read before we did this work, was there's this thing called HSTS, like strict transport security. So basically, it says you tell the browser like you shall not speak to this domain in anything but TLS for 1 year, right? So that means that they'll never downgrade to HTTP. So you can basically turn that off if you change the time on the client, right? Move them into the future or the past or something, and then they will actually move them into the future, and then they'll no longer be requesting HTTPS anymore. And then
in fact, Paul, if you want to break your home automation system, I know the brand that you use.
Yeah.
Just block NTP, and it will fail to validate the certificate when it's talking to the cloud server, and it will stop working completely. The hub will stop working completely.
Really?
You'll get a red and blue light, and it won't work at all.
It's interesting.
Yeah. My ISP all of a sudden one day decided like, hey, we're getting a lot of denial of service attacks. We don't want to upgrade our gear, so we're going to block ntp.org for everybody, for all of our customers.
That's irritating.
Everything in my home stopped working and stuff started breaking.
Wow.
Oh, pool.ntp.org. You were probably using the NTP pool.
Yeah, is that the standard pool for NTP? That's the one.
Yeah, that's the volunteer pool.
Okay.
Yeah, but there's all different kinds of servers out there. Like NIST has one. And,
Yeah,
but I was thinking, like, what does the domain have to do with this? And then I realized, pool.ntp.
Yeah, some of the older ones are actually Navy, the original.
Right, the Navy ones. Yeah.
So let me.
Yeah, Tick and Talk. Was it Tick and
Talk?
Talk? Yeah, Tick and Talk.
Yeah.
So go ahead, Michael.
Well, I mean, this is fascinating, and actually, I was luckily smart enough to follow. But so, if I wanted to go explain this to somebody else, right? You guys know my question is, where does this fit in the priorities? We're rounding out the year, going to come in the next year. There's a piece of me wondering if I'm hearing this right. I mean, we're predicating a lot of things that we trust on the internet to time. So if you can shift that time, does it undermine that trust, and does that kick this to a higher priority? And you're sitting in your enterprise today. What do you need to do about this? What do you need to know? I know there's like 3 questions wrapped in there, but let's talk maybe first about the priority and the underlying implications of this.
Okay, so I think that yes, it is kind of like the protocol that underlies many other protocols. So I believe it's very important. And I think that there are lots of things that you can do. It's sort of the protocol that is ignored because it's just, it usually works fine. That's
I set that server up 15 years ago.
It
I haven't
doesn't
had to
break.
touch it since.
Like, you really have to try to break it to get it to break. It's not just going to break because of random things. It's really like well engineered in terms of random failures, just less, attacks are something different, but random failures really, it's well engineered for the most part. So, I do believe that it needs some attention. The other thing to keep in mind is if you're running an old version of NTP, the default for all these old versions is to basically like tell everything to everyone, right? So that's why this monlist thing where you can learn all the clients, or the RV, you can learn the OS. If I send you a time query, you'll tell me back your time and your server and all these things. This is kind of the default for the way the software will run. So if you are actually operating NTP servers and clients in your enterprise, what I would do is I would really like make sure that you're not accepting queries from the outside for the first thing. Like, you really don't want random people on the internet asking you for monlist, for RV, even if you can't figure out how to configure your
amount of
servers.
effort to do that is a couple hours.
Nah, not even that. No,
I'm thinking of all the red tape I got to jump through, Huff.
What red
tape? See, you breakers come in all the time.
No, I used to run large networks. Nobody in change management could give a crap about NTP, and that's the challenge, and part of the advantage for the people that were able to configure it. The challenge being that it was assumed that it would work all the time and never fail, which is what Sharon's telling us too. And so you could tweak the configuration as long as you didn't break it. Nobody knew, you know.
Yeah, that's true. Yeah, so I think that the thing that's really important generally is just to make sure you're not taking queries from the outside. So there have been patches, for various issues. We had some teams, two different teams from Cisco had a bunch of issues that came out at the same time as ours. That are, there's a lot of interest now, actually, I think, just looking at the code because it's just interesting. There's more coming out. There was some patches came out from Google in December of last year. So they're patching and they're improving, but I don't know that it had the sort of scrutiny by security people as much. So there may be more, because people will just look for them. And there's really no reason for you to be giving out time to the world. If you're running, my laptop doesn't need to be providing time to anyone, right? So you really want to make sure that none of your devices are doing that if they don't need to be doing that, because that's going to decrease your attack surface. And then, of course, you should be patching as these patches, as the issues get resolved. But I think the very first thing that you can do, without having to understand anything, is just don't take NTP queries from the outside world. Don't answer queries. Those are called, mode 3 queries. You should not be responding to mode 3 queries. You should only take in mode 4 queries from your providers of time. Okay, so you know who your servers are. You can take queries. You can take responses from them, but you should not be, taking queries from arbitrary places. You should not be responding to any of these control queries, like monlist, RV, any of those things. Nobody really needs this information.
That's so all. I mean, in terms of actionable steps, guys, this is probably one of the simplest, most thought out, I think, that we've covered yet.
Yeah,
but that's on the edge of essentially on the edge of the network. What Sharon's talking about. What about the big Stratum 1 providers, which are doing a lot of work? The people that are running the pool, the people like NIST, the people like Navy, that truly are serving a very large part of the internet. Have they interacted with you as a result of this paper? And do you have conversations there on how to improve and help those kinds of providers on the net?
Actually, no, we haven't interacted with the big Stratum ones very much at all. So a lot of our attacks are client attacks. So what we're doing is we're trying to harm the client. So the Stratum ones really aren't clients of anyone. So they're not actually vulnerable to any of the attacks that we thought of. If you're running a Stratum 2 and you're providing time to people, then you could attack your Stratum 2, right?
Okay.
So I guess from the Stratum 1 perspective, you probably don't want to be fragmenting. NTP packets are 90 bytes long. You really don't need to fragment them, right? So you shouldn't, if anyone's doing an ICMP request to fragment, please just don't fragment. That's one of the recommendations we gave. As for the server to protect their clients. And the other thing, I guess, is to turn off a lot of these queries so that you don't reveal who your clients are. You don't need to reveal that to arbitrary, queryers on the internet. It's useful for us, though, when we do measurement studies. So if you look at our paper, we have some measurements on what's going on in the internet.
Yeah, it's useful for attackers like myself that want to attack routers, and I can get a whole list of them. It's interesting.
Yeah.
I got a different question, if I could.
Sure.
One of the things that I'm kind of fascinated with is that you've talked about the robustness of the code base and the openness of Mills to talk with you guys about this. I think it's fascinating work. One of the things that we've seen that happens with other protocols that were developed 30, 40 years ago is that people look at it and say, if we had thought about how it might have been used, we didn't expect people to do any of these things with it, but gosh, I wouldn't have done that, or I'd do it differently. Are there any lessons here then that you can pull out of it? Something that you saw that you liked and went, hey, we should do more of this? Or is there a generic lesson now for people that are creating new protocols and thinking about things that we can keep showing them time and time again of, hey, think of A, B, or C, and you'll be better off down the road?
Right. So NTP was, well, okay. So, NTP is unauthenticated for the most part. And that's a reason why all of these things, I wouldn't be able to do a fragmentation attack if it was authenticated, right? This NTP is like all these other protocols. So for DNS, we have DNSSEC. For BGP, we have the Rpki and BGPsec. Every one of these protocols now has the upgrade to the crypto version. There's now also network time security, which is cool. NTS, which is an upgrade to the crypto of NTP. So the issue with the crypto of NTP, it's been there. It's in RFC 5905. The problem is that there are two kinds of crypto. One of which is not basically the public key crypto just doesn't really work and it's not really used. There are several like actual issues with the crypto there. There was a thesis written, Stefan, I'm not going to say his name correctly, in Germany, which found several issues with the crypto, the public key crypto that's recommended for NTP, and it's basically not used. But there is symmetric crypto.
Right.
Now, the thing is that's weird about the symmetric crypto is, so basically the server and the client have to share a key. The thing is there is no protocol to exchange the keys.
Right.
So if you want the server and client to share a key, you have to like manually go and type in the key. So the way NIST does it is by fax or by registered US mail. Okay, so you can see
out of
this
band,
is pretty,
right.
yeah, this is pretty cumbersome, and so the bottom line is people just don't really use it very much.
Just curious, not to derail it, but since you looked at the crypto stuff, was the problem with the public key crypto more just about managing the certs and the trust, or was it the actual protocol and implementation? Like, was it implementation or was it code level?
Protocol level.
Yeah.
So, Sharon, tell us a little bit about your research into BGP. It's interesting, when I interviewed the members of the Loft panel, who also took home in Boston, where you're located now, when Mudge went in front of the congressional hearing and said, hey, I can take down the internet, I believe we confirmed on the interview with him and talking with him that he was referring to BGP. So I'm very curious to hear about some of your more recent research into BGP.
Okay, so interesting. That article, I was talking to the reporter that did that article as well. So, so when we talk, so shifting gears to BGP. So when we talk about BGP, it's what's really interesting about it is if you have access to a router, you can do these attacks, and we think about off-path attacks when we're network security people, like very, very powerful off-path attacks. And so like the classic attack and what you're talking about was that I have a router somewhere, and let me give you a real example. Like I have a router, this is the famous example. I have a router in Pakistan and I want to block YouTube. So in Pakistan, you guys remember this, right?
Yep.
So it's 2008. So, I have a router in Pakistan and I want to block YouTube locally in my country. And so I'm going to basically do a BGP hijack that was supposed to stay internal in Pakistan. Oops, it leaks out. And then the whole world routes to Pakistan instead of YouTube, right? So, and this is ridiculous because it's like one BGP message, right? And it just propagates through the whole internet, all the routes change, and then all the traffic will go to the wrong router where it gets dropped. And you can just basically block services that they can really not do very much about this, right? And I think that's why people kind of get worried about BGP security. It's if some place somewhere in the internet decides to hijack your prefix and that route actually leaks out and starts to propagate, then that's it. Like the traffic will go there. I mean, I to caveat that there's all sorts of different things you can do, but that's the sort of threat that we're looking at. But
you have to do those things. Like everyone who is running BGP on the internet, they have to do something to make sure that routes don't propagate that shouldn't propagate.
Right. So if you're running BGP in the traditional way, basically if let's say Malaysia Telecom wants to leak a route and their provider lets that route leak out, it'll just leak, and so people will start routing to Malaysia Telecom instead of the real locations, and those real locations is really not their fault. They haven't done anything wrong. It's not like they haven't built enough redundancy into their data centers or something. They can't do anything about it. This route has come from somewhere in the world, and it's just leaking, and it's traveling across. So depending on how the hijack happens, either they'll get all of your traffic, which was what happened in the YouTube case. What that was a sub-prefix hijack. So in IP addresses are advertised in blocks called prefixes. So when you advertise, let's say like a /22, that's 2 to the 10 addresses in that block. But that was YouTube's prefix. Now what happened with Pakistan Telecom was they advertised the /24, which is 2 to the 8 addresses. So if you've heard the word longest prefix match routing, the traffic will always go to the longer prefix. And so because the Pakistani ISP was announcing the more specific, the longer prefix, all the traffic went there, basically, everything.
Because it was a more specific route.
It was a more specific route. I mean, they could have advertised 4 /24s and replaced the /22 effectively by doing that. Right. But a lot of BGP providers now will filter to a certain length of prefix and not even accept routes when they're longer than a certain value. A lot of them do it on Class Cs to try and mitigate that issue. But all routing algorithms work on longest prefix match. So I can even go as far as to announce a /32 in the IPv4 space and say, this specific route, come to me, and it will take precedence because it is the longest prefix.
Yeah, that actually did happen. Someone did actually announce. There was an actual incident when someone announced a /32, and it actually worked. There was do you remember the DDoS attack on Spamhaus from 2013?
That rings a bell. Yep.
Yeah. So there was this ISP that actually within an internet exchange point, I think it was in the Netherlands, they announced a /32. And their neighbors inside that internet exchange point actually did route to this adversarial ISP. And what they did were they replaced the Spamhaus server with their own malicious server that just basically said that everything was spam. That was their attack. And that was on /32. So typically it's filtered. /32 is one IP address. Typically that's filtered, but sometimes it's not, and we actually have seen that people have exploited that.
Yeah, and this kind of attack actually even has applicability in the local area network space, because if you look at a protocol like ISIS or EIGRP or even OSPF, if there's no authentication in the route peering, as an attacker, you can actually play kind of a layer 3 man-in-the-middle game by announcing long prefix routes and bringing traffic to you as an edge point on the network. If the internal LAN devices are not filtering or authenticating properly. Wow.
Routing.
Is that like a lead balloon that went down?
No.
No, that's like a mic
No,
drop.
I actually had more to say.
Go ahead, Sharon.
Go ahead, Sharon.
So you asked me about my research, and I haven't told you about it yet.
Yeah, I know. We've been just okay. Sorry.
So now I'm going to tell you about BGP. So what's my research? So basically, look, people have been interested in BGP for a really long time before I even started in this business, and Secure BGP, this protocol called Secure BGP, is from 1997, which was when I was in high school. It still hasn't been deployed. It's been sort of renamed BGP-Sec and changed and adapted and improved and so on, but we're still working on this. And so basically what our research has been about for the last 10 years is kind of understanding why is it so difficult to actually secure this protocol. And I think what's really interesting about this protocol is that it's got this extremely decentralized flavor to it, and it's really sort of you kind of have to trust, you kind of just have to trust your neighbors for it to work, and that's actually the way a lot of attacks are dealt with today. So, so if something happens, what will actually happen is operators will phone each other, and they'll say, well, you did something, and the person will go and run and fix it, and that's how usually things get resolved, because it's just all these operators know each other, and they will phone each other and fix the problems. There's really no sort of centralized point of control in this protocol, and that's a really great thing, but it's also sort of really challenging when you want to do something like apply cryptography to the protocol. So for example, no one can say everyone shall now turn on crypto for BGP, which is kind of different from NTP, because you can, for example, NTP, you can update the reference implementation, right? And then everyone kind of will patch, but the BGP doesn't quite work in the same way, especially if you have to do things like get crypto keys, which you never had, right? And then the other sort of really interesting challenge is that, each one of these networks kind of makes their own local decisions on how they're going to route, what protocols they're going to use, and so on. So what we would probably expect to happen in a deployment of a security solution for BGP is we would have some networks that use it and others that don't, right? So think about DNSSEC. We have deployment of DNSSEC in some name servers and not in others, right? As things roll out, it takes time. But the thing about BGP-Sec is it's kind of this path-based protocol, right? So you have to, it's think of a graph with nodes, different ISPs, and traffic goes through all the different ISPs, and BGP tells you what ISPs you're going through, right? So imagine that only 2 of the ISPs on the path have deployed BGP-Sec, but the other 3 haven't, right? So what does that give you? What it gives you is you're still doing plain legacy BGP, right? So actually getting to the point where you have a full deployment, with a fully secured path, actually takes quite a long time. So some of the stuff that we've looked at is, how long would it take to actually get fully deployed paths given the incentive structure of the systems? What kind of security benefits do you get when you have this partial deployment situation where some ISPs have deployed it and other ISPs have not? That's some of the stuff we've looked at with BGP-Sec. And then the other really big challenge actually is that we talk about crypto keys. So how are you going to know that you have the right key? Well, it turns out that you use certificates. And so what's actually being rolled out right now is called the Rpki, which is basically a certificate infrastructure for BGP-Sec. And that comes with a lot of really interesting issues as well, because you're taking a system that's been completely decentralized and you're basically introducing CAs, certificate authorities, and they all of a sudden have like a point of control. And so that's a sort of big issue, I think, for a lot of operators that don't necessarily want to sort of cede that control to the CAs.
So Sharon, I have a question. Don't you have a bit of a chicken and egg problem because BGP enables the internet? In other words, don't you have to accept routes to communicate to the points of distribution for certificates and PKI, and thus you are talking plain text at some point in order to accept routes just to establish communication? Can you address that that aspect? Because I'm not truly familiar with BGP-SEC, so I'd like to hear your opinion there.
Yeah, we looked at that. It's really complicated. I don't think I can explain it like over here. We did find there is ways to have circular dependencies. If you have to retrieve certificates from the distribution point, what's called the publication point in RPKI speak, and your routes to the distribution point are invalid according to the RPKI, then you will not be able to retrieve the routes, right? And then you'll get stuck in this cycle. The thing is that we believe that there are ways to actually carefully engineer where the distribution points are so that it's very unlikely that you will actually invalidate a route because you can't actually reach the point where you're supposed to get the validity information for that route. So for example, if the server is serving information about a particular prefix, let's say 8.8.8, whatever /24.
The Google DNS one, yeah.
Google DNS one, right? Okay, so imagine that you have that server, and like if that's the only place, if the actual information about that prefix is only hosted on that IP address space, that would be bad, right? Because if you can't get that information, you can't actually validate that route, and you won't be able to go to the validation server and get the information, so you're stuck, right? It's a circular dependency. But if you host it somewhere else, right? So you have information about that /24, but it's hosted on some completely other /24, then that's going to give you more resiliency, right? So someone would really have to sort of destroy your access to a lot of the space in order to destroy your access to the publication point.
So the risk, so I think what I'm hearing is the risk is mitigated by having multiple peering points and potentially anycast routes in the network as well.
Yeah,
and you essentially lower the chance of complete isolation by virtue of that. Okay, that's interesting. Okay, good.
Yeah.
I think I derailed you.
No, do we talk about DNS? We didn't really talk about DNSSEC. We mentioned it briefly, but we really didn't talk about it. You wrote a paper on DNSSEC as well.
Yeah. So this paper was sort of like this problem that has been bothering me and one of my co-authors for a long time, Dimitris Papadopoulos. So I started teaching DNS in my class in 2008, and we were looking in 2010, and we were looking at the way DNSSEC deals with NX domain, which is basically saying like this domain does not exist. So, in normal DNS, if I send a query and the domain doesn't exist, I'll get a response that says NX domain, right? Mm-hmm. This thing does not exist. Okay. But now you want to do DNSSEC, right? So I send a query for some arbitrary domain name, which could be anything, right? The space of possible domain names is basically infinite. Mm-hmm. I send a query for this thing, and now the server has to respond to me somehow, right? So if it's going to cryptographically authenticate the response, there's two options. One is it's going to sign the response on the fly. So it's literally going to like figure out the answer, it's not there, and then it's going to take a key and compute the signature and respond to me. So online signing. Or what it's going to do is it needs to have some sort of pre-computed response that it can send back to me, right? But you need to be really careful, because with this pre-computed response, you want to make sure that it's not going to be vulnerable to replay attacks. Mm-hmm. Right. So if the response was this does not exist, then you could just replay that anytime, and anyone would assume that anything doesn't exist even when it does. Right. So what they do is the following. What they do is they take all the domain names. This is called NSEC. They take all the domain names in the zone. They sort them, let's say alphabetically. Okay. And then they take every pair and sign that pair. So let's say A and B exist. Let's say A and C exist. Okay. It's going to sign that A and C exists and do that for every pair and pre-compute all that and give it to the name server. So now if I ask a query for B, which doesn't exist, I'm going to get this record that says A exists and C exists, but nothing in between. So now I can validate that B doesn't exist, right? And I also have pre-computed response. So it's like a really cool solution. That's called NSEC. The problem is that now when you have these sort of like every pair being signed, and you can easily query every pair in the zone, right? And then you can learn every domain name in the zone pretty easily, right?
Can do a
That's
walk.
called,
It's like
yeah, you
a zone
can
transfer.
zone walk, yeah, zone walking. So
Zone
that's
walk.
called zone enumeration, and that was found to be a problem for various reasons, for legal reasons, for the fact that you might be exposing like machines that you don't want to expose. So what they did was they came up with NSEC 3, which was basically exactly the same as NSEC, but instead of taking the domain names and just signing every pair like that in the clear, they would take the domain name and hash it, then sort the
and then
hashes,
sign the hashes.
and then sign the hashes, right? So that was
Yep.
seen to be a way of like obscuring this information. Of course, it's just a hash, so there's dictionary attacks that have been demonstrated, and you can recover the whole zone still. So we were like, why is this problem? Like, there has to be a better solution here, right? It turns out that we were actually able to cryptographically prove that you could not solve the problem of zone enumeration and actual security against network attackers without computing signatures online. Okay, so this online signing where you actually take the query, do some kind of cryptographic computation, and then return the response is necessary. So that was like the first result, and so it kind of explained why they were stuck in this situation for so long with NSEC 3, where we knew that zone walking was possible, but it was kind of the best we could do if you wanted a pre-computed solution, or you had this online signing. So that was kind of the first thing, and then the second thing we did was we took some features of these two solutions and brought them together. So if you have pre-computed responses, the really great thing about that is that your name server doesn't have to hold any keys. So if you think about that, if your name server gets compromised, or you're using some other service to run your name server for you, you don't have to give away your crypto keys or anything like that. You can have some other secure space where you could do all these pre-computations and then transfer everything to the sort of insecure server, right? And that's with the pre-computation solution. If you're doing online signing, then you need to actually give the key to the name server. So what we have is we have a solution called NSEC 5, which allows you to do basically online signing without giving the key to the name server. So what that will do is it will give you both security against zone enumeration, so they cannot, you cannot walk the zone. Cryptographically prove that you cannot walk the zone. And you don't have to give the secret key for the entire zone to the name server and worry about that being compromised. So I can tell you the details of that. Basically what we're doing is we're using, in one word, I told you how in NSEC, what we do is we sign every pair of names, right, in the clear. NSEC 3, you sign a hash of the names, and then you hash the names and you sort them, and then you sign every pair. What our solution will do is it will, instead of using just a regular hash, like an unkeyed hash, what we do is we use a keyed hash. It's basically like a public key hash. So instead of, you take the name and you basically compute an RSA signature on that and use that as a hash. So you take this keyed hash of all the names, you sort them, and then you sign every pair. That's our solution. So now when a query comes in, what you're going to do is you're going to take the query, compute the keyed hash on the query, and look for the right pair and return that as before. Anyway, the bottom line of all of this is that all of this hashing, with the keyed hashing, is done with a completely different key, which is only used for NSEC. And that's why this key, if it's compromised, all it will do is just allow you to do zone walking, as opposed to compromising the entire zone, which is what the case is today with online signing. So we've basically split the keys. There's a key to prevent zone walking and a key to prevent network attacks. Currently, you can either sort of like expose your key to the name server, or you can expose your zone.
How backward compatible is it for existing implementations?
Well, so we are actually just working on the implementation right now. We wrote the crypto, we wrote like the cryptos on the proof. We wrote that last year. Dimitris and folks at VeriSign Labs have been working on an implementation. Also, CZNIC Labs, we've been working on an implementation for the name servers of NSEC 5. So we don't have an implementation yet. It's just really like experimental at this point. We're also working on a new protocol. So for people who are really into DNS, like you might have noticed that our signatures are a bit long because we're using RSA. We're working on shortening that length. So hopefully that will work out. So it's still really in the process. We have an internet draft. It's like a 0.1 right now. So it's not available yet, basically.
Yeah. In fact, one of the things that surprised me is that NSEC 3 has been out for quite a while, and still you have a lot of the big domains that have implemented DNSSEC still using NSEC. I remember when I wrote the zone walking feature inside of DNS Recon, two of the domains that I took for examples was Comcast, and the other was NASA. But in the case of NASA, I do have to hand it to one of their security analysts that somehow noticed that when I was writing the tool, he noticed my queries and that I was walking the zone and started breaking the chain in the zone, adding new stuff, modifying how it behaved. They never upgraded to NSEC 3, but at the same time, he did allow me to make the tool a lot better because back then there were like 4 or 5 different countermeasures for it, and he helped me kind of develop ways of bypassing all of those. In fact, every time I go back to that Python code and I look at how I handle all of those countermeasures, it's kind of like, I don't want to deal with this again. I just close Sublime, and I don't want to go through the entire logic on all of that. But I have to hand it over to whoever at NASA was looking at my traffic and modifying their zone.
They likely could be listening to the show. We're running a little short on time. Sharon, I wanted to ask you our famous 5 questions that we've asked hundreds of guests. They are the same 5 questions, so I hope you're ready.
I didn't do my homework, so I have no idea what they are.
That's good. That's the way we prefer.
All right.
Sharon, 3 words to describe yourself.
Oh my God. 3 words.
That's 3 words right there. That's perfect. See, you're an expert at this already.
Done. No, I'm done. Oh my God.
If you were a serial killer, what would be your weapon of choice?
NTP.
If you wrote a book about yourself, what would the title be?
Oh my God.
That's another time.
You should have told me. I would have done my homework. A book about myself. I don't know. Oh my God. Let's go with that.
Oh my God, NTP. You can totally combine answers from 1 and 2 and make 3. That's the secret. In the popular game of Ask Grabby Grabby, do you prefer to go first or second?
I prefer to get off the subway as fast as possible.
Okay.
Yeah.
Sharon, choose 2 celebrities to be your parents.
Ashton Kutcher and Demi Moore.
Oh, nice. That's good.
Oh, good choices.
That was quick, too. I'm impressed. Sometimes people struggle with that. Now, so when you come back on the show, we've got an additional 5 questions that we'll ask you as well. So we have 2 sets of 5 questions we like to ask our guests. So
Next time I'll prepare.
Sharon, thank you so much for appearing on Security Weekly. It's been a pleasure having you. I learned a lot from our interview, and I know our listeners are going to really dig it. So
Thank you.
thank you.
Thanks, Sharon.
With that, we're going to take a short break, come back, and talk about the stories for this week. So stay tuned. Don't go anywhere.